morning. We will continue MANOVA, multivariate analysis of variance. What we have seen in last class, that we have decomposed SSCP total into two parts, SSCP between population plus SSCP error. And we have also discussed that the degree of freedom for SSCP total is n minus 1, where n is equal to L equal to 1 to capital L n L, and there are L populations. So, the degrees of freedom for SSCP B is L minus 1, and rest as the total of SSCP B and SSCP each degrees of freedom will be n minus 1. So, the rest will be n minus L. And as I told you in last class that SSCP B will be computed using this formulation L equal to 1 to NL, NL XL bar minus X bar and XL bar minus X bar transpose, and SSCP E will be computed using this formula N1 minus 1 S1, N2 minus 1 S2, like up to NL minus 1 SL, and then SSCP T will be the sum of these two, this equation. Okay. So, now let us see one problem what we have discussed in last class, that there are three processes A, B and C, and we have sampled 10 observations from all the processes and two variables, outer diameter and inner diameter, and you see the mean values for process A is 20.20 and 6.50. So, if I write the mean values here, then for process A that mean value will be 20.20 and 6.50. Similarly, for process B it is 17.90 and 6.70. And what about for process C, that is X3 bar, this is your 20.60 and 7.50. Now, what will be your X bar? X bar will be N1 X1 bar, N2 X2 bar plus N3 X3 bar divided by N1 plus N2 plus N3. Now, we have N1 equal to N2 equal to N3 equal to 10. So, we can write this one as 10 X1 bar, X2 bar, X3 bar by 30, which is 1 by 3 into X1 bar plus X2 bar plus X3 bar. So, what will be this quantity then? 1 by 3 X1 bar is 20.20, 6.5 like this. So, your case will be 20.20 plus 17.90 plus 20.60. Second one will be 6.50, 6.70 plus 7.50. If you add all those things, 20.20, 17.90 and 20.60, quantity will be 58.70 divided by 3, it will be 1, 9, 27, then 17, then 5, almost 7. So, this quantity will be 19.57 and second one will be 6.5 plus 7.5, this is 14 plus 6.70, this is 20.70 divided by 3. Okay. So, this will be 6.90. So, this is 6.90. Okay. What more we want? We want to know what is S1, and in last class you have computed S1 is 1.51, 0.11, 0.11, 1.17. Your S2 is 1.43, 0.52, 0.52 and 0.68, and S3 is 0.93, minus 0.11, minus 0.11 and 0.72. Now, we want to calculate SSCP B first. SSCP B. If you require to calculate SSCP B, you require XL bar minus X bar and its transport to be multiplied. So, I am writing the formula. First, SSCP B as N1 equal to N2 equal to N3 equal to 10. So, I can write like this, your L equal to 1 to NL, NL is basically N1 to all those things, NL, that is the formula, XL bar minus X bar, XL bar minus X bar transpose. So, we will first consider, I think we have done a mistake, L equal to 1 to L, capital L. This is the capital L. So, our L equal capital equal to 3. So, you will be getting 3 sets of values here. First one is N1 x1 bar minus x bar, x1 bar minus x bar transpose plus N2 into x2 bar minus x bar plus x2 bar minus x bar transpose plus N3 into x3 bar minus x bar and x3 bar minus x3 bar minus x bar transpose. I will show you one calculation, first one, and then similarly other also will be computed. Now, our x1 bar, if you see what is our x1 bar, here you see x1 bar is 20.20 and 6.50. So, 20.20, 6.50 minus if we want to do x bar. So, I can say that this minus x bar equal to our x bar value is this 19.57. This is also a matrix of order 2 cross 1. Okay. So, then this quantity we can write x1 bar minus x bar is 20.20 minus 19.57. So, this is 36, I think 0.63. Second one will be 6.50 minus 6.90, this will be minus 0.40. So, what do you require? You require to calculate x1 bar minus x bar into x1 bar minus x bar transpose. This is 2 cross 1, this is 1 cross 2, your resultant matrix will be 2 cross 2, and that is what we want. So, I can write like this now, 0.63 minus 0.40 into 0.63 minus 0.40, the resultant matrix will be 0.63 square minus 0.63 into 0.40 minus 0.63 into 0.40, then minus 0.40 square. Okay, please see that these are square matrix 2 cross 2 and symmetric matrix, because this portion here this equal to this. In similar manner, you will be getting x 2 bar minus x bar, x 2 bar minus x bar transpose, and x 3 bar minus x bar this transpose. So, now the what will be the resultant value? Resultant value is this, n1 equal to 10. So, this quantity will be 10 into, we have already found out the value, 0.63 square minus 0.63 minus 0.63 into 0.40 minus 0.63 into 0.40 minus 0.40 square, plus 10 into whatever matrix value you get, plus 10 into this. So, resultant, the ultimate thing, that SSCP what you get here, SSCP will be, SSCP B will be, we have computed, that will be your 42.47 and 7.00, then 7.00 and 5.67. So, SSCP B is calculated like this. Now, we want to calculate SSCP E. I told you this will be n1 minus 1 S1 plus n2 minus 1 S2 plus n3 minus 1 S3. In this case, L equal to 3, capital L. So, we will go by like this, and n1, n2, n3 all equal to n equal to 10. So, this is nothing but 10 into S1 plus S2 plus S3. So, I will write down now equal to 10. What is our S1? You see, our S1 is this, S2 is this, S3 is these 2 cross 2 matrices. So, you write down. So, S1 is 1.51, 0.11, 0.11, 1.17. So, plus 1.43, 0.52, 0.52, 0.68 plus 0.93 minus 0.11 minus 0.11, 0.72. This is your SSCPE, and if you see that 1.51, 1.43 and 0.93, this you, if you add, what are the values you will be getting, that 15, 14, the 29 plus 9, almost 33 point something you will be getting. So, this resultant quantity will be your 34.90, 4.70, 4.70, 23.10. Okay. So far what we have discussed, if I recapitulate again, I think this is the computation part we are considering, that we said that in a MANOVA, in one way MANOVA, the SSCP total is decomposed into SSCP between population and SSCP error. And we also have seen that the degrees of freedom is n minus 1 for SSCP total, L minus 1 for SSCP between, and SSCP E is n minus L, and these are the formulation, computational formula for SSCP B and SSCP E. Then I have given you this one, this is the problem. What I said, that let us compute SSCP B and SSCP E for the data set given. For this, what you have done, you have to first find out what are the mean vectors, and these mean vectors are like this. These mean vectors are x1 bar equal to 20.20 6.50, this is a 2 cross 1 vector, 17.90, 6.70, this is also 2 cross 1, and x3 is 20.60, 7.50, this is also 2 cross 1. Using these three vectors, mean vectors, you have computed the grand mean. You have already computed the grand mean. The grand mean is n1 x1 bar plus n2 x2 bar plus n3 x3 bar by n1 plus n2 plus n3, and in our case it is equal sample size case. So, finally, it goes to this one, that x1 bar is 1 by 3 times the sum of the three mean vectors, and as resultant value is this. So, our grand mean is 19.57 and 6.90, and then we computed SSCP B using this formulation. SSCP B is L equal to 1 to L, capital L, NL into this, and SSCP E is this value. Now, from computation point of view, what we have seen, that I have shown you one computation, because the SSCP B part, if you see, it is basically sum of three different elements. Those three different elements are like this, three different elements, that is n1 into this, because see, the sum total of this L equal to 1 to capital L. So, our capital L is 3. So, if I put L equal to 1, then this is the quantity. If I put L equal to 2, then this will be the quantity. If I put L equal to 3, then this will be the quantity. Our case is equal size case. So, n1, n2, n3, I am putting 10, 10, 10, then you are computing this one. How we are computing this x1 bar minus x bar, x1 bar minus x bar transpose, that one computation formulation I have shown you. This formulation is like this. First, your x1 bar is this, x2 x bar is this, the difference will give you x1 bar minus x bar. Then x1 bar minus x bar and its transpose, this is what you have written. So, it is a 2 cross 1 matrix, this is 1 cross 2 matrix, you will be getting resultant 2 cross 2 matrix. So, 0.63 into 0.63, 0.63 square, 0.63 into minus 0.40, this will be the value, then minus 0.40 into 6.63, this is the value, and minus 0.40 into minus 0.40, this is the square value, and the resultant values are like this. So, for the first one, S1, no, this SSCB, resultant values is this, where all three parts are added, parts related to this component, this component, this component, when added you will be getting like this. Then what we require to know? We require to know what will be the sum square cross product error matrix. The formula is, it will be the sum total of n1 minus 1 is 1, n2 minus 1 is 2, n3 minus 1 is 3, because we have 3 population, n equal to 10. So, our value is like this, and we have started with this, that our S1 is this one, S2 is this matrix, S3 is this matrix. So, you are adding 1.51 plus 1.43 plus 0.93, this will be nothing but 3.49, and if you multiply it by 10, it will be 34.90, and similar manner you are getting SSCP E. So, what we have now with us? We have SSCP B matrix, which is 42.47, 7.00, 7.00, 5.60. You have SSCP error matrix, which is 34.90, 4.70, 4.70, 23.10. So, you know your SSCP total now. This plus this resultant will be 77.37. Now, 7 plus 4.7, 11.70, 11.70, then 23.10 plus 5.60, it will be 28.70. Okay. So, this is the decomposition of total matrix, this equal to this plus this, or this equal to this plus this. Okay. So, in ANOVA you have decomposed SST, sum square total equal to sum square between population and sum square error, and in MANOVA what you are doing, SSCP total is decomposed into SSCP between plus SSCP error. So, because of more than one variable, your computation will be in the matrix domain. Okay. Once you decompose the SSCPT into the parts, you are in a position to calculate the MANOVA table. Please remember, this is one way MANOVA. We are talking about one way MANOVA because we have taken only population of some kind, one kind, that population 1 to population nil, not some other kind of factors are considered. This table. In this table you have to write down what is the source, similar manner, sources of variation. So, definitely your population is one source, then error is another one, then total is coming. Then you have writing SSCP matrix. So, our case is SSCP between SSCP error and SSCP total. Then you will be writing degree of freedom, and I told you that n is sum total of L equal to 1 to capital L NL. This is the case. So, in that case our degree of freedom for total will be n minus 1, for SSCP be L minus 1, and this will be n minus L. Then in ANOVA you have found out the mean square, between mean square, error, all those things. Here we will not use like this, we will create a matrix called Wilks lambda. Wilks lambda, this is basically a ratio. Okay. This Wilks lambda ratio will be computing, where Wilks lambda is determinant of SSCP error by determinant of SSCP total. Okay. And what we want that the SSCP error, this determinant must be as low as possible compared to the total. So, this quantity will be as low as possible. Okay. Or other way you can say as small as possible, and but there are certain distribution available using Wilks lambda, and if you go by multivariate books you will be finding out that different combinations, different sampling distributions are available. We will show you a general one in this class. Okay. Now, using this, whatever we have developed so far, based on this we want to test the hypothesis. What are the hypotheses? First hypothesis, null hypothesis and alternative hypothesis. In our case, null hypothesis is there is no difference in the mean vectors for all the populations, and alternative hypothesis is at least one pair of populations are different in terms of their mean vectors. You will use a statistics, this statistics is minus within bracket L equal to 1 to L N L, this is capital N minus 1 minus P plus L by 2 log lambda. Okay, lambda, you know that how to compute lambda. Then this statistics follows chi-square distribution with p into L minus 1 degrees of freedom. Okay, so then what is our statistics? Our statistics is that n minus 1 minus p plus L by 2 log lambda, that is Will's lambda. And what we are saying, this follows chi-square p into L minus 1. What will be your decision? Decision will be, if I think this minus is the one minus is there, because Will's lambda this is a low value, keeping minus here we are making it positive. So, our hypothesis is reject H0, that means no difference among the population mean vectors, if minus n minus 1 minus p plus L by 2 log lambda, this value greater than chi-square p L minus 1. You will reject null hypothesis under this condition. Okay. Now, we will see for the problem given what is the status. You see the slide. So, SSCP B we have already computed 42.4770 like this. SSCP E is also computed, SSCP total is also computed. Our capital N is 30. So, this degree of freedom I hope there will be no problem, 29, 27 and 2, and then state statistics is lambda, and if you compute determinant SSCP E, this one 34 into 23.10 minus this square, you will be getting 784.10, and total case you will be getting this one 77.37 into 28, this you will be getting this one. Okay. So, your determinant of SSCP is 780.10, determinant of SSCP total is 2083.54. Now, if you take the ratio, you will be getting lambda equal to 0.38, correct. Now, what will be the log lambda? So, our statistics value will be minus n is 30 minus 1 minus p is 2 plus L is 3 by 2 log of 0.38. This one will be minus, this is 29 minus 2.5. So, that means the resultant will be, this resultant will be 26.5, okay, into log 38. You find out this value. I think the resultant quantity, this will be 11.25. Now, you require to find out what? You require to find out chi-square p L minus 1, p is 2, L minus 1 is also 3 minus 1, that is 2, and you have to take a alpha value, let alpha equal to 0.05. Then this one is chi-square 4, 0.05, this value is 9.49. So, statistics value is more than the tabulated value. Your case is coming like this. This is my tabulated value 9.49 and my computed value is here 11.25. This is the zone of rejection. Okay. So, null hypothesis is rejected. or we some says failed. No, this is null hypothesis is rejected. There is alternative hypothesis that there is some difference among the population means. So, as null hypothesis is rejected, so we can say that population effects are there, and now we want to know the population effect first. You see the slide. I think if you can recall my last class, then you will find out that we have computed population effect in terms of tau. Tau 1 is the population first population effect, tau 2 second population effect, and tau 3 third population effect. So, we calculate tau. How we calculate tau L? Tau L is x bar L minus x bar. So, if you want to compute tau 1, if I say this is the estimated value, then tau 1, then you have to write down what is the x 1 bar minus x bar. I think we have already seen the x 1 bar and values are there with you, x 1 bar and x bar values. Yes. Your x 1 bar is 20.20. So, your value is 20.26.50 minus x bar is what we got x bar 19 point something, I think 19.57 and 6.90. What will be this value then? This value 20.20 minus 19.50. So, this value will be 0.63 minus 0.40. So, similarly tau 2 value you will be getting. Tau 2 value also find out in the same manner that 19 point tau 2 value will be 17.90 minus 19.57 and 6.70 minus 6.90. This value will be tau 2 value will be minus 1.67 minus 0.20, and similarly your tau 3 value will be 1.30 0.60. Okay. I told you in the beginning of ANOVA as well as in MANOVA, we say that the parameters, population parameters are basically that tau L's are basically having a certain property. That property is sum total of NL tau L, this will be equal to 0. Okay. So, that means in this case N1 tau 1 plus N2 tau 2 plus N3 tau 3, this will be 0. Our N1, N2, N3 equal, that is 10 plus, so tau 1 plus tau 2 plus tau 3, that equal to 0. Now, see what is given here. What is tau 1? 1.03, 0. This is not tau 1, this is tau 3. 0.63 is tau 1 minus 0.40. So, I can say cancel 10 plus tau 2 is minus 1.67 minus 0.20 plus tau 3 is 1.03, 0.60. What the value is coming, you see, 0.63 plus 1.03, this is 1.66 minus 1.67, it is 0 basically, because of rounding error this is comes. So, this is 0. Similarly, minus 0.40 minus 0.20, that is minus 0.60 plus 0.60. Okay. So, we found out now the effects of each of the population, and we also found out that collectively there is difference. Now, we want to find out which variables are making the difference, that is our next objective. So, in order to do so, I will first show you the slide. Here I am showing you something more. What is that? That you have already found out that this is your tau 1, this one is tau 2 and this one is tau 3, other one is tau 3. So, these are all known as point estimates, correct. Now, we want to know the interval estimate of all those things. So, if you want to find out the interval estimate, then you will definitely require to find out that XL bar minus X bar, what will be the estimate, all those things. So, we have seen earlier, and in this class I will show you that as we are saying that tau 1 may be different from tau 2 as collectively H0 is rejected. So, I want to create a situation that tau L not equal to tau m, then tau L minus tau m that not equal to 0. That is your alternate hypothesis. So, what I said earlier that for individual tau L you can go for interval estimation also. We are here going for interval estimation of the difference, because that is what we want as H1 is accepted. So, now tau L minus tau m cannot be written like this, that XL bar, I am taking the estimate XL bar minus X bar minus X m bar minus X bar. Please see here what I said, that tau L is this, every population mean minus the grand mean. So, then this one is tau XL bar minus X m bar. X bar is cancelling out. So, if I want to know the point estimate of this is nothing but this one. So, you have already seen what is your this x1 bar. Suppose I want to see the value tau 1 cap minus tau 2 cap, then it will be x1 bar minus x2 bar. Yes or no? So, similarly tau 1 cap minus tau 3 cap equal to x1 bar minus x3 bar, and tau 2 cap minus tau 3 cap will be x2 bar minus x3 bar. And using the matrix the values, you can find out what are the difference values. This is not a big problem, you can easily find out. Okay. So, once you get these values, it will be point estimate. Now, I want to find out the interval estimate of the same. So, what you require to do for interval estimation, as we have seen earlier also, for interval estimation you require to know what is the expected value of, suppose tau L estimate minus tau m estimate. This is nothing but expected value of XL bar minus XM bar, what we have seen earlier. And we also know that this is nothing but expected value of XL bar plus minus expected value of XM bar, because the two populations are independent. So, this will be mu L minus mu m. Similarly, you require to compute variance component of XL bar minus XM bar, which will be variance of tau L minus tau m bar. tau L minus tau M cap. Now, variance of this equal to variance of x L bar plus variance of x M bar. You have seen earlier this one. So, this is what is the variance of x L bar? X L bar is a vector quantity. So, it is coming from the population L. Now, population L covariance matrix is capital sigma L, and it is the mean value, that covariance of the mean value. So, it will be sigma L by N L plus capital sigma M by N M. Okay. Now, you see that although I have written here variance, but you can write also covariance, because whenever there are more than one variable, we say variance structure means variance plus covariance structure. So, now in MANOVA the assumption is all the population variability is equal, this equal to capital sigma. So, then we can write this one as N L plus 1 by N M into sigma, because sigma L equal to sigma M equal to sigma, because all the population have equal covariances. So, your variability part is taken care of by this covariance part. I think in Hotelling T square time also you have seen this one. Suppose we are interested to, this is from the overall that population effects point of view, you are finding out the difference. Now, there are j equal to 1 to p variables. As I told you that I want to know what are the variables that is making the effect. So, that means tau L is nothing but your tau L1, tau L2, like this tau L p, p cross 1. When I say that tau L cap minus tau M cap, that means I say here this is tau, this L1 minus tau M1, tau L2 minus tau M2. So, like this I can get one point where tau Lj minus tau Mj, then slowly up to the last variable tau Lp minus tau Mp. If I say that tau L minus tau M not equal to 0, that means I am saying that this vector tau L1 to tau Lp is not equal to tau M1 to tau Mp. So, we have seen the variance covariance structure of this one, what I can say that variance structure of tau L cap minus tau M cap, that you have seen, this is the covariance structure, expected value also you have seen. So, I want to know also, suppose if I take a particular variable here tau Lj minus tau Mj, what will be the covariant variability and mean value for this. So, when we say expected value of tau L cap minus tau M cap, it is nothing but expected value of x L bar minus x M bar, which we say it is nothing but mu L minus mu M, then this one is nothing but, if we write down the expected value of this, okay, expected value of this or expected value of this totality, then what you will get here? You will get here mu L1 minus mu M1, like this. Here you will be getting mu Lj minus mu Mj, yes or no? So, for a particular variable case, the difference, if I see and then the expected value if I want to find out, that means what I am interested now, instead of tau L cap minus tau M cap, I am interested now with a variable that is tau L j minus tau M j. So, expected value of tau L j minus tau M j, this is nothing but mu L j minus mu M j. This is scalar quantity. Then what will be the variability part here? Variability of tau L minus tau M, that one you have seen as 1 by N L plus 1 by N M into sigma. So, we will find out the value. So, if I write down that this quantity as C, so it is basically C sigma, then what is happening? Then you are getting this covariance C sigma is something like this, C into sigma 1 1, sigma 1 2, that sigma 1 p 1 2, sigma 2 2. So, sigma 1 1, sigma 1 2, sigma 2. Where we have started? We started that C sigma is C into sigma 1 1, sigma 2 p, then sigma 2 p is coming like this, then sigma 1 p, sigma 2 p, then sigma p p. So, somewhere in between there will be sigma j. Achha, we have taken this, yes, sigma jj, somewhere in between there will be sigma jj, correct. So, for this variable what we have taken, our case is like this, for this tau L j cap minus tau M j cap, that is mu L j minus mu M j, this one the variability part tau L j minus tau M j, this will be definitely C sigma j j. There is absolutely no problem for you. That means this is 1 by N L N M into sigma j j. But please remember, we do not know sigma. What is this capital sigma? We do not know. That means we do not know sigma j j also. So, what will be the estimate of sigma cap? ANOVA you have seen, we said that, I think you can remember that MAC, we talk about that MAC is the estimate of sigma square. Okay, so here also you have found out SSCPE, if you divide it by its degrees of freedom, this is the estimate of sigma. Okay. So, SSCPE divided by sum total L equal to 1 to capital L N L minus L. This is your estimate. Suppose if we write down this one like this as W, which is nothing but W11, W12, then W1P, W12, W22, W2P. So, like this you will be getting W1P, W2P, WPP, in between somewhere WJJ. So, this WJJ, as I told you that sigma cap is estimated like this. Now, you are getting WJJ also. So, this WJJ will be estimate of sigma JJ. Okay. So, we can say sigma JJ cap equal to WJJ. So, essentially what you got now, you got very interesting things. One is your random variable, that is tau cap Lj minus tau cap Mj, and its expected value also you got mu Lj minus mu Mj, that is the mean value, and you have also got the variance of tau Lj minus tau Mj cap, that one is 1 by N1 plus NL plus 1 by N M into Wjj. So, you have everything now. Now, what do you want to know? We want to know the interval estimate of this, that is what we have started. So, interval estimate of please remember, this is a random variable, the mean interval estimate for the mean we want to compute, not that interval estimate of this. With the help of this, we want to compute the interval estimate of its mean value. So, what you want Lj minus mu Mj, you want to create an interval, correct? Okay. So, what will be that interval? You see now that we will go by Bonferroni approach. Why we are interested in Bonferroni approach here? You see the slide. Okay. See the slide here. Now, how many comparisons possible? How many comparisons possible from the variable point of view? You see there are L populations, you are comparing 2 at a time, then L into L minus 1 by 2 will be the number of comparisons, because if there are 3 populations, 3 into 3 minus 1 by 2, that 3 comparisons. If there are 4 population, 4 into 4 minus 1 by 2, that is 6 comparisons possible. 6 comparison possible means 6 mean vectors comparisons. Now, we are comparing again the variables. So, the p values are coming. How many variables are there? P variables are there. So, in total you have m comparisons, but what you want an interval here L and U in such a manner that this will probability of this less than L less than equal to this equal to 1 minus alpha in such a manner that you will achieve 100 minus 1% confidence interval, that should be simultaneous, that should be simultaneous. Now, we have seen earlier in our two variable two population case that there are two approach, maximization lemma and your Bonferroni approach, and Bonferroni approach is easier. So, we are considering Bonferroni approach. In Bonferroni approach, what happened? What it is basically first saying that okay, how many comparison, that means how many mu Lj minus mu Mj, that is m equal to p L minus 1 L. In our case, it is p equal to 2, L minus 1 will be your 3 minus 1 into 2 divided by 2, divided by 2. So, it is 4, p is 2, 3 minus 1 this 2. So, 4 comparisons possible, 3 comparisons. P is how much? P is 2. Oh, L is 3. So, this is 6 comparisons. L is 3. So, is 6 comparisons simultaneously you have to make. So, our alpha, it is a two-tailed case, T distribution will be using two-tailed, this side alpha by 2, this side alpha by 2, but what happened, we have 6 comparison, that Bonferroni says you divide it either equally or with certain weightage we are dividing equally. So, that means alpha by 2 m, and this side also alpha by 2 m, correct. So, then if this is the case, so what you require to know now, that means we are creating a T statistic here, and your T statistics, the degree of freedom will be n minus L, and you are considering alpha by 2 m case, because m comparison is there, okay. And you also multiplying this with what, the variability component. What is this variability component? 1 by NL plus 1 by mm into Wjj. This one will be subtracted, that portion will be subtracted from x Lj bar minus x mj bar, this minus this. So, this is in the same manner the way we have done earlier also. We know the distribution, then the critical value, and we multiplied with the variability. This will be less than equal to mu Lj minus mu mj less than equal to x bar Lj minus x bar mj plus T n minus L alpha by 2 m into the variance part. Okay. So, in this manner you have to find out the difference, that is what I said, the confidence interval for the differences, and then you find out which difference contain the mu. That means, under null hypothesis there is no difference. So, mu Lj minus mu mj will be 0. If you find out any interval this side or that side, this value plus this value, it contains 0, then that variable is not differentiating. Okay. Suppose the difference will come for a particular variable, let it be minus 2.50 to 1.30. Then see, and within in between there is 0. So, this variable is not creating the difference. Suppose some value is like this 2.50 to minus 1.30, yes, this is a differentiating variable, or 1.45 to 1.90, that is correct, that is also different. So, 0 is not there, means null hypothesis is not satisfied with this interval, because we have created T distribution, T values mean that 0 will be there in between. Okay. I think this is what is one way MANOVA, and you have seen in totality like this, that you are comparing several population means, then coming to the conclusion that the population means differ. Then you are trying to find out that which of the variables are causing this difference. You are going for the interval estimation of each of the variable for different pair of comparisons. Then find out which are the variables creating the difference. Okay. And next class I will show you one case study. Okay. Okay. Thank you.